Welcome to the lecture on transient response analysis. In this lecture, we will continue our discussion on underdamped second order system. So, in previous lecture, we saw that an underdamped second order system has certain response characteristics and its response overshoots the final value. So, we can see that the response of an underdamped system is, so this is T, this is Ct, and if this is the C final, so the final value it overshoots, then it comes like this. So this time Tp is the peak time, this is called peak time, and this is C max, that is C max, maximum value of this response at this peak time. So we see that the peak time we find equal to pi upon omega d or pi upon omega n root 1 minus zeta square, where zeta is damping ratio and omega n is natural frequency. So the here response Ct was, for this system we derived, was 1 minus e power minus zeta omega n t into cos omega n root 1 minus zeta square t plus zeta upon 1 minus zeta square sine omega n root 1 minus zeta square t, or this also we could write 1 minus 1 upon root 1 minus zeta square into e power minus zeta omega n t into cos omega n root 1 minus zeta square t minus phi, where phi is tan inverse zeta upon root 1 minus zeta square. So this was the response for this underdamped second order system, and we find peak time by taking the slope of this curve equal to 0, that is dct by dt equal to 0. Now we have to find the percent overshoot of this system. So percent overshoot is the value, how much this maximum value go beyond this final value, that is how much it overshoots. So percent overshoot is defined as C max minus C final upon C final into 100. So maximum value minus this value, so this quantity by dividing the final value. So first we have to find this maximum value, and that C max will be equal to C t when t equal to Tp, because this Ct equal to Tp, because at t equal to Tp the value we will get is the maximum value. And so if we use this formula, this expression, so we will get, and Tp equal to pi upon omega n root 1 minus zeta square, so we will get 1 minus, so e power minus zeta omega n Tp, and here t equal to pi upon omega n root 1 minus zeta square, that will cancel out, and so we will get cos pi, and cos pi is minus 1 here, plus when here it is 0, because here sin pi is 0. So we will get here equal to 1 plus, because minus minus plus exponential minus zeta omega n, and Tp is pi upon omega n root 1 minus zeta square. So this equal to 1 minus e power minus zeta omega n into Tp is pi upon omega n root 1 minus zeta square. So here omega n will cancel out, and we will get 1 minus, sorry, this is plus 1 plus exponential minus pi zeta upon root 1 minus zeta square. Now this final value is 1, because we are considering this response for unit feedback, unit input function, step function. So here C final equal to 1. So we will get percent overshoot equal to C max, that is 1 plus e minus pi zeta root 1 minus zeta square, and minus 1 by 1 into 100. So here into 100. So that is equal to exponential minus pi zeta by root 1 minus zeta square into 100. So this is the percent overshoot. Now here we can also get from here, we see that percent overshoot is only the function of damping, and so if we want to see the, and when damping is more, this quantity is less, so percent overshoot will decrease when the damping will increase, and that is likely because the role of damping should be to decrease the response amplitude of the system. So therefore more damping, less overshoot, so less maximum amplitude of the system. So here we will get something here, let's say this is 100, this is 50, this is 0, and this is damping, and this is percent overshoot, and damping is varying from 0, let's say 0.5, 0.9 something. So here percent overshoot at when damping is 0, this is 100%, and then it will start decreasing exponentially, negative exponential, and it will meet somewhere here. So we can see the exponentially decaying this quantity. Now here we can also write the, from, we can take log and we can write damping here, and that is minus ln percent overshoot by 100 upon pi square plus ln square, ln percent overshoot by 100 So we can also express damping in terms of percent overshoot. So we take the natural log and we solve this to find the damping, and we will get this value. So we have discussed this percent overshoot. Now the next parameter. So here we have discussed the percent overshoot, the amount that the waveform overshoots the steady state or final value at the peak time, expressed as a percentage of the steady state value. So this is percentage overshoot, and this is the damping in terms of percentage overshoot. Now we come to other parameter like settling time. So I define the settling time is the time for the response to reach and stay within plus minus 2% of the steady state value. So here we can see the TS here. So here it is reaching at value 0.98 of the final value, and it stays between 0.98 to 1.02 of the final value, that is 1. So here 0.98 to 1.02. So here response, so this the time when it reaches to 0.98 of the final value is, we call it settling time, and the settling time we can find. So we can find settling time C TS 0.98. So it is 0.98 if our, and then we can write here, let's use this formula. So 1 minus 1 by root 1 minus zeta square exponential minus zeta omega n Ts cos omega n root 1 minus zeta square Ts minus phi. And from here we will get that 0.02 equal to 1 by root 1 minus zeta square exponential Ts cos omega n root 1 minus zeta square Ts minus phi. See this, the value of this term is, maximum value is 1. So we can have e power minus zeta omega n Ts by root 1 minus zeta square equal to 0.02. And from here we can find Ts, that is equal to minus ln 0.02 into root 1 minus zeta square upon minus zeta omega n. So this is the settling time, and so this value for different values of damping zeta, when we vary zeta from 0 to 0.9, this value, this term, the numerator term varies from 3.91 to 4.74, and therefore some approximate value we can take as Ts equal to, so this value equal to 4, so 4 upon zeta omega n. So we take approximate value 4 between these values, when, because here the this term is very small, so its effect is less, and so we, this term we approximate as 4, and this term is zeta omega n. So settling time is 4 upon zeta omega n So we will have, so settling time is we can define, and we find that Ts equal to 4 upon zeta omega n. Now we come to the rise time, and rise time is defined as time for the response to go from 10% to 90% of its final value. So here we can see the response here is this 10% here, so 0.1 of C final, and it reaches here 0.9, that is 90% of C final. So this time TR is called the rise time. So rise time here is plotted, rise time into the natural frequency for certain data. Refer to the book of NICE, NS Control Systems Engineering. So here we find this relationship for the rise time. Omega n TR equal to 1.76 zeta cube minus 0.417 zeta square plus 1.039 zeta, and this is found for damping between between 0.1 to 0.9. So here we have this relationship. So if we know the damping and frequency, we can calculate the rise time for the system. So we understand that for underdamped system and underdamped second order system, we have 4 characteristics that characterize the response of the system. So there is peak time, percent overshoot, settling time, and rise time. So these are the specifications that we can demand when we design this second order system, that how what value we want for these specifications, and we can design our system. Now let's show the on the S plane this underdamped system, the poles, and we see how what will be the effect of the movement of the poles on of the second order system. So we can represent on the pole this S plane, these poles. So it is sigma and j omega. This is S plane, and we have underdamped system. So we get the poles S12 equal to minus zeta omega n plus minus j omega n root 1 minus zeta square. So these are the poles of an underdamped second order system, and we also call them minus, let's say, sigma d plus minus j omega d. So here omega d is the imaginary part of this pole, and sigma d is the magnitude of the real part of this pole. And so sigma d is called exponential damping frequency, exponential damping frequency, because it decides the exponential decay of the amplitude of the response, and omega d is called the damped frequency of oscillation, damped frequency of oscillation. So this is the frequency with which the damped system oscillates, and you can see that this is less than the natural frequency, because this damping is greater than 0. So, this value will be less than 1, and therefore, the damped frequency is less than the natural frequency of the system. Now, if we want to plot this, so here is minus sigma d or minus zeta omega n, and we have here, so these are the two poles, and this is j omega d, and here is minus j omega d. So, we can see that this is origin, and so if we plot this line, what will be this radius or the distance from origin to this pole? So, let us say this is O, this is A, this is B, this is C. So, OA equal to this square plus this square. So, zeta omega n square plus omega d square. So, that is omega n root 1 minus zeta square whole square. So, here we get zeta square omega n square plus omega n square into 1 minus zeta square, and so we will get here omega n square minus omega n square zeta square will cancel out. So, we will get omega n square here OA square. So, OA equal to omega n. So, this is omega n. Now, come to this theta. So, if we calculate cos theta, so cos theta equal to this quantity zeta omega n upon OA, OC upon OA. So, this is OC upon OA, and OC is zeta omega n and OA is omega n. So, this cancel out, that is equal to damping ratio. So, here theta equal to cos inverse damping ratio. So, it means this theta shows the damping of the system. So, here we can see now these things are clear. So, theta equal to cos inverse damping or damping equal to cos theta. Now, we know that Tp, the peak time, equal to pi upon omega d, and settling time is equal to 4 upon zeta omega n. So, that is equal to 4 upon sigma d, because zeta omega n is sigma d. So, we can see that settling time is function of the real part of the pole and peak time is function of the imaginary part of the pole. So, now let us see what happens when these poles, there are some poles, this pole sigma j omega, and we have these complex poles, and these poles start moving in this direction. So, if these poles start moving in vertical direction or parallel to the imaginary axis, what will be the response of the system. So when these poles are moving, we can see that so this is theta 1, this is theta 2. So theta 2 is greater than theta 1, and here one more quantity we can write percentage overshoot, that is so exponential minus pi zeta by root 1. So we can see that theta 2 is greater than theta 1 here, and sigma d is constant because this real part, that is sigma d, is constant, it is not changing. So sigma d is constant means settling time is constant, and theta 2 is greater than theta 1 means we have, and cos theta 2 is less than cos theta 1, and so damping 2 is less than damping 1, because here damping is equal to cos theta. So theta 2 is greater than theta 1, so cos theta 2 is less than cos theta 1, so damping. So we have less damping here, when we are moving we have less damping, and so your percentage overshoot is more. So percentage overshoot for 2 is greater than percentage overshoot of 1. And when we are moving from here to here, omega n is increasing. So omega n2, omega n1, so omega n2 is greater than omega n1. So we have natural frequency that is increasing. So settling time is constant, Ts is constant, same, that is same. So here we can see when we are moving in the vertical direction 1, 2, 3, and this is a response of the system here 1, 2 and 3. So we see that we have the same envelope, because envelope is decided from the sigma d, that is exponential damping frequency, because it comes as e power minus zeta omega n, that is e power minus sigma d, and sigma d is constant, therefore that envelope will be constant. So here envelope is the same. However, we can see that for the peak time of the third pole position is more than second than first. So peak time is depending on the omega d, and we can see that omega d is increasing. Here is omega d 3, omega d 2 and omega d. So this is 1, 2, here 3, this is 2. So omega d2 is greater than omega d1. So peak time will decrease for the last one, because the omega d3 is even greater than omega d2. So peak time is inversely proportional to omega d. So here peak time is decreasing. Now come when the poles move parallel to the real axis farther from the origin. So we have omega d constant, so we will have peak time constant. So this we can see here, this peak time is for constant. However, we see that less overshoot, because when we are going farther, the cos theta, the theta is decreasing, and so cos theta is increasing, therefore damping is increasing. So due to increased damping, there will be the less overshoot. So therefore overshoot of second one is less than overshoot of first one. Now we come to the case when poles move in radial direction. So when poles will move in the radial direction, we can see that this is the constant, this damping line, because theta is constant, so your damping will be constant, and therefore percent overshoot will be constant. So we can see from this curve we have the same percentage overshoot. However, the peak time is also decreasing, because we are moving in radial direction, so we are also increasing the omega d, that is the imaginary component, and so your peak time is inversely proportional to omega d, and therefore your peak time will also decrease. So here uh, we stop our discussion on underdamped system. So we saw that the underdamped system, they have a response that oscillates, but there is the amplitude is decaying with time as an exponential function, and we derived this formula for the peak time, settling time, overshoot, rise time, and we saw what will be the effect of the movement of the poles in three different directions and how the response will change. So this we related the pole position with the response of the underdamped system. So I stop here and see you in the next lecture. Thank you.